This Explain Everything video is intended as an instructional resource to help teachers more effectively conduct the lesson as described in the teacher notes. The same acceptable use policy restrictions apply to this video as they do to the rest of the curricular materials made available by AMTA. Now that we've studied various intermolecular forces, it's time to examine the factors that affect the miscibility of liquids. Miscibility is a property of substances to mix in all proportions. For example, ethanol and water are miscible, whereas oil and water are said to be immiscible. These two examples lead to the generalization, like dissolves like. Ethanol and water are both polar substances, therefore they dissolve in one another. But since oil is nonpolar, it will not mix with the polar water. The following demonstrations allow us to test this generalization. In this picture, you see three graduated cylinders in which different liquids have been placed very carefully so as to form distinct layers. The relative positions of the layers is due to the differences in the densities of the substances. First, we'll examine the contents of the right graduated cylinder. The bottom layer is water to which blue food coloring has been added. The middle layer is methanol, which is left colorless, and the top layer is pentane, to which a few crystals of iodine have been added to give it a reddish purple color. Of these three liquids, water is the most dense with a value of 1.0 grams per milliliter. Methanol, with a density of 0.79, floats on top of the water, and pentane, with a density of 0.63 grams per milliliter, floats on top of both of them. Mu is the symbol for dipole moment, which is a measure of the polarity of the substance. From these values, you can see that water and methanol are polar, whereas pentane is not polar. Take a moment to predict what will happen if these three liquids are mixed. Based on the generalization, like dissolves like, which liquids would you expect to combine with one another? The three liquids are thoroughly mixed by shaking the graduated cylinder. Then the layers are allowed to reform. Note that the purplish pentane layer is about the same size as it was before, but the methanol and water appear to have combined. This result seems to bear out the generalization that like dissolves like, because both methanol and water are polar, whereas the pentane was not polar. Now we'll examine the middle cylinder. The bottom layer is colorless dichloroethane, the middle layer is water with some blue food coloring, and the top layer is the reddish purple pentane colored by iodine. The density of dichloroethane is 1.25 grams per milliliter, so both water and pentane float on top of it. Based on the generalization, like dissolves like, predict what you'd expect to happen when these three liquids are mixed. The three liquids are agitated and allowed to separate out into layers as before. Observe carefully. From the size and the color of the layers, you can determine which liquids combined. The bluish water layer is now on the bottom, and it appears that the pentane and the dichloroethane have combined, forming a liquid with a density less than that of water. This result contradicts the generalization like dissolves like, because the nonpolar pentane dissolved in the polar dichloroethane. Some other factor must be involved. Perhaps polarity is not the important factor in whether liquids are miscible. Let's look at the Lewis structures of the liquids that did dissolve in one another. Not only are water and methanol polar molecules, they are both capable of forming hydrogen bonds. While dichloroethane is a polar molecule, neither pentane nor dichloroethane are capable of forming hydrogen bonds. So, while water and dichloroethane are alike in that they're both polar, they're unlike in the fact that water can form hydrogen bonds, but dichloroethane cannot. Perhaps miscibility depends on whether the liquids are capable of forming hydrogen bonds. We have set up a third case to test this new variation on the generalization, like dissolves like. Here we have blue-colored water on the bottom. On top of that is colorless acetone. Both of the liquids are polar. And on top of that is our purplish-tinted pentane. From the Lewis structures, we can see that both water and acetone are polar, but acetone is incapable of forming hydrogen bonds. Knowing that water and acetone are alike in that they're both polar, but unlike in their ability to form hydrogen bonds, you might try to predict what will happen when these three layers are mixed. As before, the cylinder is shaken to mix the three liquids and then set down, allowing layers to reform. Note that the bluish water layer is larger than it was before, but the pentane layer is also larger. Apparently, the acetone dissolves in both the pentane and the water with a partition ratio of about 1:4. What can we learn from these three demonstrations? First of all, don't overgeneralize. The like dissolves like rule is too simple to describe solvent miscibility. Multiple factors must be taken into account. While all molecules that can form hydrogen bonds are polar, not all polar molecules can form hydrogen bonds. As it turns out, most organic solvents are intermiscible, whether polar or nonpolar. Therefore, there's nothing that prohibits polar liquids from dissolving in nonpolar solvents. Why did the methanol show a preference for water over pentane? That's because the interaction due to hydrogen bonding is so much stronger than the general tendency for alcohols to dissolve in organic solvents. When hydrogen bonding is not involved, then the generalization that the closer the polarity of two substances, the stronger the interaction is between them applies. So polar acetone is more likely to dissolve in water than in the nonpolar pentane, but that doesn't prohibit some of the acetone from dissolving in the pentane. So, as we said before, recognize that generalizations have limitations. Molecular polarity is not the only factor that governs miscibility. Hydrogen bonding is also important. Miscibility should be viewed as a continuum rather than a dichotomy. It is more useful to describe the extent to which one liquid will dissolve in another than to say it will or it won't.